From the outside, a dull mill looks straightforward, but inside, transforming a raw seed into an edible split grain is a violent, high-friction physics problem. To remove the outer skin, the grain is pressed against a heavy carborundum emery roller. The efficiency of this process depends on a concept called the kinetic baseline. If the internal bearings supporting these rollers wear down unevenly, the machine enters a rotary kinetic deficit, where the rollers lose their perfect alignment. When the rollers tilt, the friction becomes uneven. Smaller grains escape the rollers entirely, while larger grains are trapped by the asymmetric pressure and instantly pulverized into worthless dust. This microscopic misalignment creates a massive financial leak. A typical mill can lose between 5 and 15% of its total product strictly to this unnoticed grinding error. In a high-volume facility, this unseen friction acts as the primary silent killer of the factory's profit margin. Most mills defend against this with preventive maintenance, a calendar-based strategy where machines are shut down on a fixed schedule for manual inspection. This traditional method is expensive. It requires a large labor force to perform the checks and forces the mill into planned downtime, stopping production regardless of whether the machine actually needs repair. The critical flaw here is that human eyes cannot see internal mechanical wear while the machine is active. This leaves the operator guessing about the health of the hardware between scheduled checks. This creates a dangerous blind spot. A bearing can develop microscopic fatigue just days after a manual check, causing the roller to misalign and destroy thousands of dollars in product for weeks before the next inspection. By relying on a rigid calendar, the mill remains structurally blind to the real-time degradation of its own equipment. To eliminate this guesswork, modern mills are moving toward predictive maintenance, a system that replaces manual inspections with automated, real-time monitoring. Piezoelectric sensors bolt to the bearing housings, listening to vibrations from the spinning rollers. An edge AI analyzes these signals to establish the acoustic signature of a healthy baseline. If a bearing starts to fail, the wave pattern spikes instantly, long before the roller misaligns. The system then generates a precise time-to-failure alert. This allows the mill manager to fix the specific component during a brief, targeted intervention, preventing the grains from fracturing. Predictive data changes the logic of the factory floor. Instead of reacting to a breakdown, the mill proactively defends its kinetic baseline. Keeping machines in a state of continuous perfect calibration causes an immediate surge in the volume of usable product. This chart shows how that precision translates to profit. In a 50-ton mill, preventing just a 1% loss to powder recovers 500 kilograms of sellable product every single day. Traditional dowel mills are labor-intensive, requiring a large staff to manually watch for leaks, listen for belt slips, and check individual starters. By centralizing this oversight through sensor networks, A high-capacity mill can transition from 15 people roaming the floor to just 3 operators managing the entire system from a digital interface. This efficiency extends to the power grid as well. By catching kinetic friction early, the system prevents motors from overdrawing electricity, significantly reducing the factory's energy consumption. Predictive monitoring is more than a software update. It is a force multiplier for the physical efficiency of the entire plant. This transition reflects a broader philosophy known as restorative engineering. The goal is not to replace human capability, but to bridge the gap between digital software and the unforgiving reality of physical hardware. This approach significantly delays mechanical fatigue, maximizing the service life of heavy equipment and preventing the unnecessary waste of raw agricultural materials. The most effective systems operate in silence, using intelligence to protect the physical world from its own friction. The most profitable mills operating today don't just hope for a high yield, they treat the final product as a mathematical certainty, the inevitable result of using digital intelligence to master the physics of the machine.